Okay, hello everyone. Thank you for being here. First of all, I want to thank the CMS team for giving the opportunity to the Beamline for School participants to join this webinar and to join this online event and to be able to visit CMS virtually this time. For all the attendees, you can type your questions in the Q&A and the CMS experts will be answering your questions. So I think this is all. I hope you enjoy it. And well, I will give at the end, maybe, I will talk a little bit about Beamline for Schools. But just in case, check our website. You will be receiving a lot of emails from my side, and we are going to start from next week more online events, and just be tuned because we will be presenting the competition for the next year in the coming weeks.
Okay, so I guess it's our turn. Welcome everybody to the CMS control room, and nice to meet you. I am Giulia. I'm a PhD student from Italy, and I will be giving you the guide today from the surface. Together with me, we have to my left Zoltan, who is the expert and co-founder of this virtual visit setup, and Noemi, who will be with you downstairs in the cavern of CMS. So welcome everybody. I think we can start with a slide showing you where we are geographically and what we're doing here. And then we will bring you around our control room. Okay, first of all, what you see here is the LHC. So the yellow ring is the collider where we have our particles running through and colliding in the points that are the experiments. In particular, we are here to the far left in the CMS point. CMS is one of the big detectors of the LHC, is one of the two that were designed mostly at the beginning for discovering the Higgs boson, which was found in 2012, and now we're doing different kind of physics. Let's say the interesting aspect about CMS is that it's a multi-purpose detector. So we basically are able to see almost all fundamental particles, and we can reconstruct a lot of different kind of physics. So where we are on the surface. So you see here CMS, it's the first one to the left. It's also called 0.5. We are right now on the ground, so we're not yet underground. And you can see that CMS, the actual experiments, which lies down here, it's the deepest one, as far as I know, out of all the experiments of the LHC, and it's more than 100 meters underground. Now, I think, well, this is a picture of our beautiful CMS. It's the most colorful one, by the way. On the top right, I think we can walk around the control room if Noemi gives me the okay. So I will show you basically the place where we're sitting right now, which is the spot where we have all the screen and displays to control what's going on with our detector. Okay, let's walk around. So first of all, we have the setup, let's say the chairs of the technical shifter, TS. You can see the letters up there. This is the person that checks the status of the detector. So basically, this is a health check. You can see that we have on the top cameras, for example, to make sure that no one is underground while there's physics ongoing. As you might imagine, when there is beam on, we clearly cannot access the experiments. So it's really important to have, well, we have a lot of safety systems, but good old looking, watching at cameras helps a lot. And you can see also that they have on the left screen with a bit of like green. This is to see which part of the experiment is, let's say, on, is off, is working or not working properly. If there is any issue, an error pops up here. And I would say for the technical shifter, that is pretty much all. You can see, well, the technical shifter and the acute shifter working in front of here. So this is like real life experience for you. We have a lot of activities planned for this morning, and you will be a bit seeing like the activity around here. We move on. The next step or next stop is the shift leader. The shift leader, SL, which is Francesca. Ciao, Francesca. Is the, let's say, the fundamental person that keeps everything together. So the shift leader has to keep track of how all the detectors are doing, or of what the physics program for the day is. So she will be able to coordinate with everyone. You need to imagine that we have like a lot of experts, up to probably 20, 30 people that are at home but have phones and can be called 24/7 just to see if there's any problems or similar. So the ship leader is the coordinator of all of that.
Captain.
The captain of the ship. And as you can see right now, we have, well, we are in ion physics. You see the screen on the top right. So right now we're not colliding protons, which is the activity we do mainly. It takes up almost the entire year. Right now we're doing ion physics for mainly for ELIS, but we do take data as well. And we have right now no beam. So for the moment, there is no physics ongoing downstairs. It will start again in the afternoon or probably tomorrow. You must know that the beam is not continuous. So first of all, we have usually 7, 8, 9 months per year of beam. Usually we do not work with the LHC in winter, because it takes up a lot of energy. And in winter, when there's the heating of the villages and the light is up for more, it's quite hard to sustain both the LHC and the, let's say, winter life of Geneva. And also, when the LHC is running every day, we have, let's say, 11, 10 hours of beam, and then we have a tiny stop because the beam deteriorates, so protons needs to be stopped and then injected again in the LHC. So that was the shift leader stop. Let's go to the DAQ. Noemi is showing you the spot. Here we have another friend of ours, Costanza, who's the DAQ shifter today. And well, the first thing you see is the rubber ducks, the plastic rubber ducks. We're a big fan of them because, as you might imagine, it's just a matter of sound, DAQ, which means data acquisition, sounds as duck. So this is, let's say, the mascot for the DAQ shifter. Data acquisition means that this person here, this shifter, is the one responsible for the entire CMS taking data. So basically, she has right now screens. You can see a big all OK. Screens reporting the status for all the parts of the detector. So every single little piece sends its own data. There is checks telling us if the data are fine or not fine, if there's any error that occurred. And if not, the state of the system is running, and we have the beautiful big bright color green. And you might imagine that we run continuously, but that's not actually pretty true. So we have often, let's say, slight hiccups. You need to imagine that we are reading hundreds of thousands of channels. So it is, let's say, statistically, one of them will break every once in a while, and then we need to intervene as quick as possible. That's why we have also people that are on call 24/7. We move on now to the trigger and DQM. Trigger first. Okay, now I need you to bear with me. The trigger concept is, let's say, not the easiest. So what you see here are a set of plots related to the trigger decision. How does that work? We have one collision every 25 nanoseconds. So we are running very, very fast. And in each collision, we have, well, let's say in each time that the two proton bunches cross, we have several collisions. And recording all of those data would be crazy. So we would really have too much data, and that's not sustainable. So what we do is basically we select events that are potentially interesting, and we store them while we discard all the rest. And we discard the more than 99% of the data. You really should imagine that we need to take very good decisions very fast, because most of it's going to be lost otherwise. An example of an interesting event, well, if you think of the Higgs boson, the Higgs boson can decay to muons. So when they were looking for the Higgs, and also right now, what we do is we look for events that contain 1, 2, 3, 4 muons, and we select them as interesting. And this is the role of the trigger and trigger shifter. So the trigger shifter is the one making sure that all of this is working very nicely. We then have the data quality monitoring, also known as DQM. This is a very fast, on-the-fly summary of everything that is going on. So basically, you see right now that most of the stuff is green. This is beautiful. It means that every single channel of every single system is sending out good data. For example, we might have, I don't know, a part of the detector that switches off. It actually happened to my subsystem throughout the night because there was a tiny leakage. Well, at this point, you will see that the system is not sending data anymore. So you will have a red plot. The DQN shifter will see the red plot, will trigger an alarm, and will start calling the people that are responsible for the part that has broken. So as you might understand, well, there's a lot of, let's say, effort and rush in order to try to take data 24/7, because also the LHC beam is expensive. So we need to make sure to make the most of it and take, let's say, every single collision that we can. And this control room setup is exactly how we ensure this. And now we're actually stepping to our own spot.
So I have one technical comment. Just try to keep talking another 5 minutes. I try to get a replacement to help Noemi. As you probably all know, one person alone cannot go down.
I know.
That's one of the. No, it's not for you. You know it. Much better than I do. But we do not, for safety reasons, we do not allow a single person to go down.
I have the dosimeter and mask and everything if you actually want.
Yeah, but in that case, I need to talk.
You don't want to talk? You like
I do it regularly, but anyway, it doesn't matter.
No, I'm kidding.
So Catarina was so kind to offer to help us. She needs a little bit of a time, so probably let's.
I can go to the shop.
Yeah.
But then tell her, contact her. She went back to the meeting. Actually, we are running the weekly meeting on technical coordination matters, and she works for the safety.
Oh, okay.
She needs to be there, but fortunately she can escape. She is a very kind person. You will see her soon.
I will explain CMS from the picture so that they have a clear, better understanding later. So now you have the theory part, but you will see some actual pieces of detector soon. Hold on with us.
Yeah. All right. So we apologize for this little of glitch, but you see we are professionals and we are going to.
And maybe just to remember the students, you can type on the Q&A your questions. So you can ask whenever you want. This is for the students.
Yes, feel super free actually to ask any question that you want. As I said, I'm a young PhD student. I will try to answer as best as I can. Zoltan next to me is actually a lot more expert than me in CMS.
I can tell lies as well, yeah. So very.
We're going to the Peter Sharp room, where it's another room on the surface where we have some samples, some pieces of the detectors. So some pieces of the CMS that's actually downstairs. We have some spares, and we will be able to show you how it works, let's say, before you actually go down. So you have a clear idea of what pieces are inside. So, okay, thank you, Noemi. Now, what we're seeing here is a piece of the tracker. So the inner part of CMS, now you need to imagine pixel. Well, that's not my expertise area. I call them like...
Neither mine.
But, okay, fair enough. So what we will show you is basically CMS from the inside out. So CMS is, let's say, an onion. So there is a collision point at the center, exactly, and the particles come out from there. And basically, what we have is an inner part, an inner side that allows us to track particles, so to actually follow them step by step and see where they're going. So for example, if they are in a straight line, if they curve or not. After that, we have two colorimeters, which are the light blue and yellow parts, which measure the energy. Then we have a magnet, which is useful for bending the particles. And in the outside, we have muon detection, because the muons are the only particles that can escape all the material that is before them. So now we will see, first of all, as I said, the inner part, so the pixel and the tracker. The pixel is a set of silicon sensors. So they are made of silicon. They're solid sensors. It's not like a gaseous material. And what this is done for, as you can see, it's super tiny, but this is a microscope enlargement. And as you can see, there are so many channels. Why? Because as I said, we're trying to track particles. So we want to know basically by the millimeter and even more, the precision of where the particle passed. This is let's say, a grid. So you will be able to follow, for example, electrons in a first layer, second layer, third layer. You put them all together as shown in the picture here, and you have the overall track of a particle.
We have to confess something here.
We have to confess something.
Yeah, actually, on this phone, no, we are not showing that camera. On this phone of mine, I have a camera with 120 megapixels or 200 megapixels. Who knows? Many megapixels.
Many megapixels.
Much more than what we have here on the pixel detector. However, this is arranged on a single chip, the many megapixel in my camera, on one flat surface. In our detector, we have, I think, 4 concentric barrels.
Even, probably
so that can give you a 3-dimensional resolution.
Exactly.
And there is a minor difference between these two. While my phone can make in burst mode, can take something like 10 pictures per second, while our can make 40 million
pictures per second. So also, this is what I was talking about with when I was saying that we have a lot of channels that we need to take care of. So we're constantly taking data from all of those single bits, and there's many more downstairs. Oh, yep. Here we have another piece. Exactly, that's a strip, and that's a strip of the NCAP, am I right?
No, this is a barrel leather. Okay. But below that, I think that's the.
Oh, yeah, okay, yeah. Yeah, that's the NCAP, because well, as we said, it's CMS is cylindrical, but we do not have, let's say, holes at the 2 ends. We need to cap them. So we literally have 2 caps that are called end caps that are basically circular shapes that are used of detector, that are used to close the holes at the ends of the cylinder in order to be able to detect particles over there.
I just want to use the nice physicist word. We are hermetic.
We are hermetic, which is almost true. There is the tiny gaps.
We want to catch as many particles flying in any directions out from the collision point. So that's why we had to build something that surrounds as much the interaction point as it can be. Obviously, by the beam pipe, the particles might escape. Around the beam pipe, the radiation is very high. So the technology when we built the detector was not there. Now we are approaching. We are installing new detectors closer and closer. They can survive. But obviously, the hermeticity will be broken at the beam pipe at some point. Although we have detectors outside of the CMS volume, the CTPPS, that is several tens of, maybe hundreds of meters away from the interaction point, down in the accelerator tunnel. So if you just look at this, as we call it, pseudo rapidity, it is nothing else but the tangent of the particle flight path. That's they look like as if they were in the beam pipe.
Exactly.
Right. Sorry for. But one more thing I would like to say, and that's the reason why we have the cylindrical onion. Not because of its stinky. No, it's not.
It's not stinky.
The thing is that usually when I used to talk to my visitors, I used to say that I have to confess. I have to confess something.
Okay.
There were several Nobel Prizes awarded because of the particle physics discoveries in the past, let's say 30 years. The first was the for the W and Z boson discoveries sometime in the mid-80s.
Yeah.
And recently, something like 10 years ago, the Higgs boson was discovered. The thing is that even though these particles do exist, we know that they exist, they are very short-lived. So it means that that you cannot see them flying through the room. They will decay characteristically something like 10 to the minus 20 something seconds. So even if they would fly at the speed of light, they would not travel more than the diameter of a proton. So it means that there is no chance to see them in their physical reality, but if they decay to something. So what you can do to measure these decay particles, measure the parameters of these decay particles. What parameters do you want to measure then? Of course, where they fly away, the track. You want to measure their momentum in some cases, you want to measure their energy, and also you want to measure or guess their identity. Actually, that's quite important to know that if it is a
muon
or a okay, Giulia will do it for me. She's much younger than I am. No, she's young. I am not. So, indeed, if you just consider that on one hand you want to measure the flight path, and on the other hand you want to measure the energy, you get to a completely different measurement strategy. Yes. While in case of measuring the flight path, you don't want to interact with the particle. Of course, you have to, otherwise you will not sense it.
But you don't want to destroy it.
Exactly. You want to minimize this. You want to build a lightweight detector. That's also a very, very loved expression about it. So you want to make something that makes keeps this interaction to the minimum. While on the calorimeter side, the aim is to take away all the energy from the particle. That means you want to absorb it. And turn it to something else.
The particle.
So obviously, what you can consider that if we wouldn't talk about anything else but this, this would be enough to tell that one homogeneous detector material is not enough for what we want. So that's why we have these
layers.
Yeah,
let's say.
And then I just give you
about what Zoltan was saying. So remember what we were talking about, and especially what you saw. The inner parts, so let's say the tiny sensors that you saw were part of this silicon tracker.
Image.
Okay, they were this small silicon tracker. So you can see there are basically layers of those sheets full of sensors, so that you can really track the particle in X and Y, so in the space, and also in the three-dimensional direction, so you can see where it was going. While Zoltan talked about stopping the particle afterwards in a calorimeter, well, first we have the ones that is called the ECA, so electromagnetic calorimeter.
You are from ECA.
I am from ECA, so this is my beloved one, which is used to stop particles that interact in an electromagnetic way. So for example, the electrons or the photons. After that, you have the HCAL, which is the much bigger yellow one here, which is used to stop hadrons. So basically bigger particles that interact differently. So not electromagnetically, but with strong interactions. After that, you have the superconducting solenoid, which is used to bend particles. Why? If you have, for example, an electron flying, you
don't hear them. She's explaining how it's going.
Oh yeah,
we hear
I know
you
Noemi.
instead.
We're getting. This is good news. Nice. We're getting our guide.
Yeah, and it would be nice if you could show the
calorimeter
superconductive thing. So obviously that's the ECAL, I guess, on the right. Yeah,
that's exactly. The ECAL on the right. Well, you see a red.
Yeah, just from the top.
Exactly. You can see on a red support a big rectangular crystal. The ECAL, our calorimeter, is made of lead, so a very heavy material because you need to stop particles. but you need to, basically the particles make light when they enter those crystals, and you need to collect the light. So this is actually lead tungstate,
Can I show this?
and it's completely transparent. It's also extremely, extremely heavy. If you were here in person, you would be allowed to like press a lever and see how heavy one of those crystals is. Well, it is really impressive. It's really
can go
impressive,
back
at
to
least
that.
to me, that lead-based something is completely
I
transparent.
think the single glass is sodium silicate or something like.
Yeah, yeah.
If you replace the sodium with lead, you get the lead silicate, which is often used in the kitchen.
Okay.
Even my mom made me a dish in these very nice, also transparent things. But if you move even further and replace the silicon with tungstate, then
Then
you
you
get
have
here.
the
This is
scintillating
heavy
heavy. Yes,
stuff,
exactly.
and of course poisonous.
Oh, definitely. But I mean, we don't eat them or we don't lick them
No,
or
definitely.
anything like
We
that.
know how to deal with.
Yeah. So, well, the ECAL is basically, you need to imagine it as a layer of crystals where when the particle enters, it showers. So, for example, an electron will emit a photon, which splits up into electron and positron and so on, and will leave its own light there, as you can see basically in the picture on the left, and the particle will die there. After that, we have the hadronic calorimeter, the HCAL, which is designed completely different. Basically, it's not made of crystals. It's made of layers of brass and scintillating materials. So the idea is that instead of having a single material that can both stop and collect the light, make light, and then gets collected, here we have the brass on the top and the plastic scintillators on the bottom. So basically you do it in steps, let's say a bit of stopping, a bit of light, a bit of stopping, a bit of light. And this is how we detect hadrons. This part of the calorimeter is much bigger. We have a lot of energy to record. Actually, it would be probably nice to have it even bigger because the particles that we're trying to detect have a very, very, very high energy. So it's very hard to actually stop them completely inside our volume.
Actually, when you design a particle detector, I mean,
you need
an
to,
experiment,
yeah, exactly.
This is one of the key parameters you have to keep in mind, that your calorimeter should be as thick
as possible.
Enough thick to be able to absorb the highest energy particle that is created in your experiment. So that's if you think about to design a particle experiment, then probably this is something that you have to keep in mind. Also, I have another fun fact with the HCAL.
Okay.
Since the HCAL is made of brass, I mean copper and
other I know things, that. It's fun.
Oh yes, exactly.
No, go for it. No, you go for it.
If there are radionuclides, many radionuclides in these materials, you see it as a noise, a background noise in the detector. Obviously, you want to minimize it as much as you can. So we try to find a brass that was made before the nuclear age, and that's what you see on the picture. So you see the late World War II brass shell cases from the Russian army, Soviet army.
Yeah.
So that's something. That's the way how we keep the peace.
Fair. taking away guns to make detectors.
Yes, exactly. That's a good. So you know that there was another direction when the bells of the church towers were confiscated to make cannons.
Oh yeah.
This is the opposite way. I'm much more like this.
Yes, fair enough. These guys is actually really interesting because, well, the CERN and LHC and CMS experiment is a big scientific effort, international community, but it's also like tightly woven with the history of the time that we're going through and the availability of resources around us. So I mean, we are we have to interact a lot with the outside world, and politics influences us and everything. So yeah, that's an interesting aspect. Science is not completely out of the world.
Actually, that's one of the reasons why we are here today.
Yeah, fair enough. Well, let's get back to the physics. So what Noemi is showing you right now is this light blue layer in my picture, which is the superconducting solenoid. So what is a superconducting solenoid? Basically, a solenoid is, let's say, a cylinder.
Just a technical thing from
Go
me. Noemi texted me. Of course, we are in connection with her.
Okay.
And she says that a visit is going to start in that room. So I would propose for Noemi to go out. We have another setup in front of the PM54 with that, and we can continue talking about this. If you agree. And in the meantime,
but just show this.
Try to just try to keep this photo in your mind, and we are going to talk about why Noemi arrives there. Okay, let's go ahead, Noemi. So this is a superconductive material. We need to have, in order to bend the particle path, the charged particle path, to measure momentum, obviously we need a magnetic field. What we produce inside the magnet volume is extremely strong, 3.8 Tesla, something like 100,000 times more than that of the Earth magnetic field. And in order to do that, you need to have some super tools. And the super tool is the superconducting material. When this magnet was designed, and even up to today, the most widely used superconductive material is a niobium titanium. And that's what we are using. And what you remember, what you can recall in the middle of that slab, that was the niobium titanium superconducting material, encased in copper for technical reasons. But what you can, that's what Noemi shows now. This Barbie hair is the niobium titanium itself with awful mechanical properties. That's why we have to do some trick. But what you saw, that a relatively small cross section there, and that small cross section can lead 18,640 amps. In order to create the 3.8 Tesla magnetic field. That's what you see in the middle of these slabs. And this is embedded in aluminium. There are two different types of aluminium. You might see from the shining of this material. The two side slabs are purely for mechanical stiffening, but the one that really encapsulates the superconductive material is, on one hand, an insulator. I leave a couple of seconds to digest this, that an aluminium is an insulator. On superconductive temperatures, when the niobium titanium starts to superconduct, that is with really zero resistivity, everything else that has a non-zero resistivity becomes an insulator. But once we lose the superconductivity, the aluminum turns on, it increases the cross-section, therefore decreases the Joule heat that is resulted by this enormous current, and that gives us a little bit of a time to dissipate that energy that is stored in the magnet, 2.2 gigajoules in case of CMS. We bring it up on surface and dissipate on a resistive network. Otherwise, we would boil up the helium around and we would blast off the moon. I know the moon projector, something very popular today, but not this way.
Yeah, exactly. Maybe we would blow up our detector. But
surely, that would be a disaster. You would hear about it. We want to avoid.
Definitely. It's a very delicate equilibrium to have everything working at the, let's say, in this very hard and harsh condition. We're really stretching everything to the limit. And well, stop to think about the age of the electronics and systems and technologies that we have in the detector, because everything was built almost well, in 2012 the Higgs boson was discovered, so you need to think that like 5 years before that everything was in place, and so it was designed even earlier. These things come from the early years of this millennium, basically. So yeah, it's really impressive to have everything here if you think of how fast technology upgrade is and has been through the last years. But our old beautiful CMS is holding up very nicely with a lot of maintenance on our side, but it's working. And
probably the best place in the universe.
Yeah. We do not have, I think, where Noemi is, but she will confirm anything muon. Let's
We
say.
had in the previous room.
Yeah,
actually,
exactly. A part of muon.
So definitely, what we can say about the muon detectors is, first of all, the calorimeters work perfectly.
They stop almost particles.
Everything. Only 2 particles are not. But what we know about the particle list of the standard model of particles at this moment.
Yeah.
That was the footnote. So what we almost all the particles are stopped by the calorimeters.
Yes.
Except 2. One is the neutrino. The neutrino, just a weakly interacting particle, obviously. This flies through the detector. That can fly through the sun even.
Yeah, actually, they fly through us and through Earth every day.
Billions of neutrinos every second. So, but definitely it doesn't interact with the detector. We see it as a missing energy, but we know that missing energy is not a physical thing. That's just a detection. And the other particle that's very, very important in our case, in our discoveries, is the muon. The muon also can fly through even hundreds of meters of rocks. So that flies through our detector, but as it is charged, it can leave a trace in a charge-sensitive detector. It can leave a trace inside the tracker,
exactly,
but also outside, away from all the others. It can leave a very nice trace in the muon detectors. The muon detectors are, in our case, gas ionization detectors. It's not needed to be that. It could be silicon completely, but nobody has such an amount of money. So and also the resolution is not needed that a silicon detector can provide, but the good old gas detector, I hope my colleagues around will not kill me immediately. That's one of the nicest development part of the physics detectors. I myself work for another gaseous detector, muon detector. So obviously I would need to myself. Okay. Anyway, let's just get over with this logical thing. So they can make an ionization in these gas chambers, and we can detect the electrons that are created by this ionization. At this moment, I wouldn't go deeply in, as Noemi and Catarina are just taking their place in the elevator. Yes, she is Catarina. And then what I would say, what I would say, we are going to lose her soon, in a couple of seconds, as the elevator goes underground. Obviously, the wireless connection will be broken, I think at 3.2 meters deep. No,
0.9. Well, this elevator goes down 100 meters. So now they're gonna go down 100 meters. There's a fun fact that we always talk about with the CMS elevator. This is the safest place in case, for example, of an evacuation or anything. You are told that you mandatory need to take the elevator, which is kind of particular if you think of like any other place in the world. It's
completely the opposite.
The reasons, well, there's multiple reasons. The, let's say, trivial one is that stairs for 100 meters is very long. So if there's a very big emergency, probably you don't want to be running for 100 meters up. But then there's actually a much better reason for that, which is that the elevator is pressurized. So there is a slightly overpressure inside the elevator. So basically, if there is, let's say, a leakage of any gas that you cannot breathe and is poisonous, this will not enter inside the elevator because the air will naturally be pushed out of it. All right, now you see that we have them back.
They are heading down to -3.
Yes.
That's 97 meters below the surface. And you are right when saying 100.
You go in first.
We have another something below the detector, something like two more levels. Today we cannot go there for a very simple reason. There is no Wi-Fi there.
Yeah, fair enough.
So if our people would go there, you wouldn't see. So it's better not to send them.
What you see.
We need a key.
Yes, it is happening now. You might see.
Yeah, it's not really probably visible, and you probably don't hear it.
I go and help them.
But there is let's say an alarm sound going off, which was triggered by the fact that they are trying to access on the yellow door downstairs there. And basically, the controls for everyone accessing is centralized. So everything is done by up here by the control room, because we really, really need to make sure that no one gets stuck down. So basically, we had some person back there manually approving their access. This is what opened the key cabinet that you see here that Noemi is now showing us. So now you will see one of the, let's say, one of those tiny doors popping open, and there, yes, exactly, there will be a key here. Each single person has to take a key, so every person inside is tracked, and we cannot start the beam if the key is not returned. Now, Noemi is entering, the doors will open, and there is an iris, I think, recognition, or anyway, eye recognition here, which you will be soon looking at.
If
Oh,
I
yeah,
don't
okay.
make a mistake.
It's actually super sensitive when you go in. You, for example, you cannot bring material, you cannot bring a backpack. You like there's a lot of let's say sensors that make sure that you're not bringing in someone else. There's a head count. So yeah, it can be tricky. You might need to take some minutes to enter, but now that was successful. No, that was not.
Okay.
In
the
the
meantime,
meanwhile,
yeah.
yes.
Did you tell them about that these iris scanners check for
I
the
try
blood
one more
circulation?
and then
check for
blood circulation as well.
No, really? That I didn't know.
I know that our audience is very young.
Yes.
But there was a movie somewhere at the first half of the 2000s called Angels and Demons, where without telling the full story, they went down in the LHC tunnel. I flew, by the way, and they did something trick to the iris scanner, and they went in, and that was the way how they stolen the antimatter to blow up the Vatican. So
yeah, okay, that cannot
the
have
script
like,
is very weird.
Yes.
But indeed, we used that type of iris scanner. So the movie makers made a complete access point like what you've seen today. Of course, not at Geneva, but they also made some tournage here at CERN. But they used the same equipment that we used that time. But in order to completely screw up the script of this movie, let me just say that this new version checks both eyes and the blood circulation in the eyes.
Okay. Wow.
And I'm not going to spoil the complete stuff. All right. I hope Noemi is already in.
Yeah, everyone's in. So now you are seeing that they are down in the tunnels.
She just leaves all the valuable stuff there.
Yeah, exactly.
But you will see.
We have the magnetic field on.
This is what I want.
Yeah, exactly. Oh,
it's a surprise. So definitely we have the magnetic field. You can see. Well, I think we
have some indicators.
Yeah, exactly. We have a very expensive magnetic field indicator. Please don't forget that these expensive tools are hanging. Okay.
Yeah.
Yes. So look at them and remember
Let's go
them
in
right now. A fun fact is that you see that they're crossing a lot of corners. They are doing that because in order to stop radiation does not go through corners. So we have concrete hallways that always have corners so that if anything happens or there's a radiation coming out, you simply need to literally enter one of those corridors, walk a bit, and then you will be safe. So it's a containment measure and a safety measure.
But on the other hand, if there would be a fire in there, and the fire brigade would need to enter, obviously, if they would break in through the system, first of all, the pad would block the full accelerator, all the 27 kilometers. And these chicanes are designed such a way that by the time they would jump in, as Noemi and Catarina just did, the radiation level would go down enough to make a minimum thing. Okay, so now you can see
the magnetic field in action. This is a real simple chain and a simple key that, and you see that they're not hanging straight because the magnetic field is extremely strong. It's almost 4 Tesla inside. It's still a lot of Tesla outside.
No. What they see is a couple of tens of millitesla.
Yeah, exactly.
So
It's still so strong
exactly.
that you need to imagine that, for example, when we need to go downstairs and do like some work, I don't know, we bring a hammer or something, that needs to be not magnetic because otherwise it would fly out of our hands. Oh, this is impressive. Noemi is having a lot of fun.
Oh yeah, and she has the ducklet. That's a little ducklet.
Let's try to fly the duck, the small duck.
No.
So she has the duck fly.
Okay.
Oh yeah, the camera moves because we had to remove it from the gimbal that we use normally on the surface. The gimbal wouldn't survive this magnetic field. We tried.
Oh no.
Oh wait, it
one.
just stopped working.
Okay.
So fortunately we didn't need to buy again. Hey.
You see that it's standing.
Well, oh yes.
Well, you see that it's actually flying.
Actually, that's the point where we used to lose the guides on the ground.
Yeah, because they just play.
They feel the magnetic field. They continue playing, and the visit is screwed up. Yeah.
But okay, let's also take a moment to talk about the big orange thing that the guides while playing are.
Also, it's really hard to remove from the the floor because that's also
usually
iron.
what we don't advise the guides. These tools might stick on very strongly. Fortunately, she didn't use the. Oh yeah. Fortunately, she didn't stick it on the edge of the red slab, right to her.
Otherwise, it would never.
At the edge, we have half a Tesla. So if she would do that, it would require quite an effort to separate again. Obviously, we do not leave it in there.
Yeah.
For the operations.
May I talk about this orange stuff, what you can see down here?
Absolutely.
So that's, I don't know if you see it. This is on one of the feet of this big structure. And this is the tool where we can move this big element. Each of them is some thousands of tons heavy. And we have 4 of these orange stuff. They can put in very pressurized air, and it could lift up a little bit. So it's like a hovercraft. They put some grease on the floor, and then they can attach a wire to the edge of this element. And with relatively a small machine, we can show it with Catarina, they can move it. Of course, the motors has to be synchronized because you want to move the things in parallel, but the machine itself for the big thousands of objects is relatively small with compared to the size of the CMS. But you can see all the cables for moving of these objects, because we have to open it when we want to reach the detectors which are installed inside. So everything is hermetic, everything is compact, and the bad thing of this that we cannot reach easily our detector. We need really an engineering work to open it. And if I remember, it takes some weeks to reach.
This is the price we pay for.
Yeah. And what you see.
In contrary, let me just. Oh yeah.
Okay.
Sorry, go ahead, Noemi, and then I do.
I just want to show you that this is also a detector. This is a calorimeter, a very forward calorimeter for the small angle outflying particles. But what you see here, the orange stuff is just the shielding. It's for an extra shielding along the beam pipe to stop all these particles which go along the LHC beam, because that is, of course, it's a noise for the detectors which is inside, and we want to detect the particles which are coming from the interaction point, from the interaction, not the other particles.
I have just seen a talk about it. This extra shield is pretty new. We installed this one that you see in front of you last year, and on the other end of the experiment a year before, we already have some very interesting noise measurements of the immune system, and I saw the curves, very convincing.
Really? Okay,
Yes.
changes.
But actually the main reason, from a detectorist point of view, like I am, this is something. But on the other hand, there was another indication for making these guys that's also related to the radiation. This radiation that makes our detector radioactive. You might see that we have quite a lot of tons of iron around. We try to buy an iron that is depleted in cobalt. So the cobalt 60 as an induced radiation would be as much as minimized as possible. But in the steel production, the manganese is a material, is an additive material that you cannot miss, and that creates manganese 54 that keeps radiating after the detector, of course, in a decaying way. And of course, we are not talking about a nuclear power plant or a nuclear blast, but this is something that we can measure, and this is something that we have to keep in mind when we access the detector. So it means that if these shields were not be there, we would need to wait a couple of more months before we open the detector.
Yeah, and it's not feasible, not affordable with our timelines in general. Like if
we are working on your tax money, so
yeah.
obviously.
Is this the end of the big shaft or the small shaft? Can we
Yeah,
see
the big shaft.
This is the big shaft, I think.
So if they turn the camera up, they see a black hole. That's the black hole that we have.
That's not a black hole. Well, first, I will explain what this is. Then Zoltan will answer one of the questions of the group where they asked about the black holes. So this is not a black hole. This is just the vertical tunnel through which the detector slices were sent down. Our detector was built over the surface, so basically next to where we are here now in the control room, and it was built in slices. So you need to imagine that you have the cylinder and you slice it, and each of those slices was then lowered down into the cavern. There's a few fun facts. We will be seeing.
If I find the mouse, one slice.
Yeah, exactly. You see it also here on the top right. Those are literally the slices that were lowered down. As you can imagine, it is extremely heavy and extremely big. And the shaft was just a few centimeters larger than one single wheel. So every wheel was lowered down, and it took hours and hours. I think about like 12 hours. Oh, okay, 8 hours.
Because
otherwise 40 seconds would be
talking
enough.
About the lowering.
Oh yeah, that's the gap that you see on the right. The green structure belongs to the detector. On the left, the green structure belongs to the cavern.
So you literally see that like it's like the width of a hand, no more than that. So really, it was also in terms of civil engineering, it was really, really a very big effort to lower the detector down, and it's extremely heavy. It's 14,000. Yeah, exactly.
14.5. Some other sources tell about 12,000.
Okay.
So this is hell heavy. What we used to say that this is approximately twice as heavy as the Eiffel Tower. And twice as heavy as the Atlas detector, which is twice as big in each direction, so 8 times bigger volume. The Atlas would float on water. I already proposed to wrap it in cling foil and put it in water, but Atlas colleagues wanted to
did not want to do that, right?
Yeah.
Well, you can imagine the reason. Like you see them in the picture here, but it's not in scale. Atlas is really much bigger, and the reason why it's much lighter is that it has a lot more gaseous detectors than CMS. So
Also
basically,
different
completely different field, magnetic field
exactly, and
carrier.
and the different philosophy of measure.
Yeah, absolutely. And there is actually a very interesting and nice physics reason behind all of this. So you only have a single place on Earth that's able to produce, for example, the Higgs boson. And if you do a single measurement with a single detector, what is there to tell you that it was not like a fluctuation or a statistical thing or just a human error? So you need to double check the measurements, and you do this by building two detectors that have a completely different philosophy. So they do not have the same biases and same errors. And what happened is that we saw the particle with a completely different strategies, both in CMS and in Atlas. So that's how we can call it.
But as a consequence, as the Atlas is lightweight, their magnetic field configuration is different. They have quite a lot of beams, I mean mechanical beams to hold the detector together. That induces an inequality in the field.
Yeah, the field is uneven with respect to CMS is super beautiful because it's a solenoid. The field inside is perfect.
It's perfect. It is designed. The magnet is. I mean, these red slabs are designed such a way that inside the red slabs we have a saturation field 2 Tesla. So it is 2 Tesla. While in Atlas you have inhomogeneity. That's the word I'm looking for. I'm over 50. The inhomogeneity of the field might introduce measurement errors. Obviously, they measure this inhomogeneity to the absolute nicely. This is one of the best such a detector at Earth that is known to this level. But if we think of the momentum measurement of the muons, for example, their systematic error is dominated by this. In CMS, we don't have such a systematic error.
We do have other problems. The calorimeter is
no. Just in the muons, since we have a lot of material, you might have such a situation when the muon collides with the nuclei and therefore changes a little bit the flight path. So that's what we call multiple scattering. In our case, the multiple scattering is dominating the systematic error. But if the two experiment at the same time in the 4-lepton 4-muon channel decay of the Higgs boson, the invariant mass becomes 125 GeV. In both cases, you might be absolutely sure that the systematic errors do not have an effect on your measurement.
Exactly.
And that's why we are there, and that's why we are so much different. Sorry, I think we just didn't allow Noemi and Catarina to talk. And at the meantime, I would like to ask the attendees that if you have any question that is related to the detector cavern, please ask it now. Otherwise, I will let them to come up.
Yeah, fair. Yeah.
Yeah, we just went up to make a nice overview of the detector size. It's about 4 level building, the height. So of course there are not so many people in the cavern, but you can see the size from this view.
I think I will go down in less than half an hour.
And just previously we tried to show you the feet of the detector to see how big is one big object. So
yep.
Okay, so
right. I think you could gradually
come to the control room. Okay.
Exactly. We keep your picture on. And in the meantime, we got a question, a very exciting question. Yes. And the question was that why, according to Einstein's theory of relativity, can't microscopic black holes be created at the LHC? We would be very happy to create black holes at LHC, not just because we are so crazy and fatalist that we want to kill the full universe this way, obviously not. But according to the general relativity, it might happen that you can concentrate such a large energy in a very small volume that might turn into a micro black hole. And since Stephen Hawking, we know after his work, we know that these tiny little black holes, actually all the black holes evaporate. That's due to the physical behavior of the event horizon and also the quantum mechanics. In quantum mechanics, the vacuum is not empty. You might get particles and antiparticle pairs jumping out from the vacuum. These are virtual particles. They disappear almost immediately. But what happens if one of the pair appears on one side of the event horizon, while the other is on the other side of the event horizon? Obviously, the one that goes inside will never come out. That means that the one that comes on the outside should be realized. So the realization takes energy from the black hole. Okay. That's the evaporation. According to the theory, this evaporation rate is inversely proportional. I don't know to which power, but inversely proportional to the radius of the black hole. So the smaller the radius, the faster this evaporation is. And those black holes that we hoped to create inside our detectors are so little tiny that they would decay in the very fraction of the second. So they would not be able to collide with the beam pipe and get more energy and finally eat up first the detector, then the Geneva region, and then would go even further, despite the video that I saw on the YouTube 10 plus years ago, where the black hole surfaced at the very point where I used to park my car in the parking lot. But
nice.
Yeah, exactly. I didn't park there for 2 or 3 months. But
okay.
Actually, I think you are sitting at that very point now.
Oh, nice,
in this
because
new
it's a new
building. Yeah,
room.
exactly. But anyway, that was just a joke, of course. What we would expect that these black holes would evaporate extremely quickly. They would have a characteristic pattern left in the detector that we would see. We had simulations how it should look like. The bad news is that we didn't see it yet. Yeah, but that means that even if they can be created, they can be created at an even higher energy or an even larger energy concentration. Don't forget that the problem is, and that's, so far I told something that I read, now I tell something that I speculate. I have to tell, but these black holes would be so tiny in our case that they would be somewhere at the Fermi length. So I would say that for that we would need to create an enormous energy. Very probably the LHC is too big to do that. We need a new accelerator. Please pay from your taxes. The accelerator that can go down to really the Planck energy, or Planck length, not Fermi length, Planck length. That would be something like the size of the solar system with this technology.
I don't know if tax money is gonna get there.
Yeah, but that is a message to the audience that please invent a new technology and please go work towards to this. Okay, message over. Noemi?
And Noemi is getting back.
We're just changing back to the
upstairs setup.
Gimbal. Yeah.
Yes.
Yeah, we don't want to feel bad, the audience.
And
yeah, while we
and people are.
How you go, Noemi?
Yeah, people are just coming in, so we have to wait until we can go out.
Don't worry. Let's just continue.
That's nice. You guys are seeing actually like activity ongoing. There is actually a lot of people right now in the control room.
Yeah, and I said that sooner or later I will have to go down as well for the
chat. Really, today?
Yeah. We are inspecting.
Just in case, there are 3 questions in the Q&A from students.
Oh, sorry.
If you want to answer them.
Yes. What are the restrictions in terms of the objects or materials that a researcher can bring inside the facility if the CMS is running? If the CMS is running, you can't go in. That's obvious.
But I mean, right now the CMS is on. We don't have the beam running, so we don't have physics ongoing. And you
That's
can
true.
bring down objects and materials that are compliant. So like no like hammer that is made of iron that is magnetic. So like there is a set of tools, as far as I know, that you can bring down and that are made available. When the magnetic field is off, you can actually access a lot more easily because, well, of course, we need often to bring down, I don't know, electronic boards and screws and screwdrivers to install them and everything like that.
I would just reverse this question.
Okay.
Not what to be able to be taken in, but how
What-
can you bring things out?
Oh, that's fair.
So obviously that you take in by yourself during an access, you can bring out, but every pieces that have seen the beam, that were in the detector, installed on the detector or were in the detector cavern during the beam was on, should be considered as radioactive material
Yes.
by legally. And in order to be able to bring it out, first you need a radioactivity measurement by professional RP experts, and they will tell you how to handle this equipment after all. They might release it, so you can use it if it is
Not active
it is not
anymore.
active. But if it happens to be active, you have to follow the corresponding rules. This is very strict. We do not want to emit any radioactive material in the environment.
No, absolutely.
And this is also checked by not only by our RP specialists, but also the authorities of the host countries. I've already seen people working here from France, the startup guys. They check systematically the trash bins every night.
Okay.
Yep.
Okay, fair enough.
This is one thing, and I also seen Swiss environmental radioactivity measurement equipment on the countryside, just outside CERN, far away. I saw them measuring. So we are also tracked by the host state authorities. So we have to play absolutely fair.
Second question that we have is what were the major setback or challenges that we've encountered in the operations of CMS in the past year? Well, the first huge setback when the LHC, actually not CMS, was switched on but Zoltan probably knows better than me because I think I was in elementary school, was the explosion.
I was already an assistant teacher at the university that time.
Really?
Yeah,
Okay.
I was at home, sitting in my lab at home and listening to the news. And the news at noon was telling that the LHC was stopped because it exploded. And I didn't want to.
It's not as bad as it sounds.
Exactly, but I didn't want to believe it. So I immediately turned on the Vista page and I saw, yes.
It exploded.
Yeah, exactly. There was a technical problem. I wouldn't go into details. That's also very interesting and something that we learned a lot from there. But I would like to tell something for the setbacks or a problem that might happen with such an experiment, and we are just starting to see. In the past, the particle physics experiments didn't last more than 10 years.
Yes, we are lasting 20 years.
Exactly,
and more.
And another 20 is ahead.
Yeah, exactly.
So what we might have is the aging of the materials, the aging of the connectors. So we
already have it. Like in ECAL, you can already see that the radiation that the detector is taking has already deteriorated it enough that the resolution that we have is not as good as it was the first day it was
exactly
built.
the yield goes down.
Yeah,
get darkened.
The electronics is really at the
but that's going to be replaced.
Yeah, it's going to be replaced
the next year, next technical stuff. So definitely these are the things. The aging is a setback, and aging is something new that we started to see, and we have to somehow to mitigate during the next years. One of the things that so this is one of the reason why we are going to very heavily use the long shutdown 3 that is due to start mid next year. ECAL is going to replace the electronics. That's one of the biggest project that's going to happen.
Yes, there is also the insertion of completely new detectors because we said it's a cylinder with the end caps. As the beam arrives from here, the highest radiation levels are concentrated in the end caps because the particles cross each other and spread in that direction. The end caps, for example, for the calorimeter, would be completely replaced. Both ECAL and HCAL in the end caps would be removed and substituted by a much more resistant and
Not just that,
higher
but also
performing calorimeter.
Exactly.
It will be a high granularity calorimeter, so we will have a much better understanding and resolution of the particles that we see inside it. This will be because we will have a lot more collisions per single punch crossing, and we need to be able to tell every single of them apart. Now we have like around 60 at peaks, and in the future we will have up to 200. So it's like almost a factor 4 of increase in what we call pileups. So let's say collisions going on top of the other.
I
of
have
each
a
other.
pileup picture. Yeah.
Oh, that's a pileup picture. Each point is one of the, let's say, collisions, and you see, well, this is quite interesting. Like you see that from every point you have traces coming out of it, and what we need to do is, like you have the detector up here, you need to basically reconnect every trace to this point in space and time where it happened. So it's going to be a really interesting and challenging time ahead. And we're preparing for this. This will happen in, I don't know, like 3, 4, 5 years.
Yeah, but actually what you might see a lot of green lines, but one blue and one red. And as far as I recall, that these are the interesting physics, and all the others are just simple collisions.
So we need to discard a lot of stuff, and we need to be very good at doing it. And it's going to be even more challenging than it is now to discard all of that. Yeah. There was a fun other question about the fire extinguisher.
That was a question about the fire extinguisher.
We do have real fire extinguishers, probably the ones that you saw.
Quite a few different fire extinguishers. What you've seen is with the green handle, I think, on the top.
Possibly.
Yeah, because you know why it's green?
No.
Because it's magnetically insensitive.
Okay.
Because normally a fire extinguisher would immediately stick on a detector. These fire extinguishers that we have are either carbon dioxide. That's very good to extinguish almost any fire. Or additive to water. Such a way that you could even use it for electric fire up to 1000 volts. That's most of the detector. But apart from this, we have sprinklers, we have carbon dioxide,
and we have the foam injector.
And we have actually very famous foam.
This is a much more than a simple fire extinguisher. In downstairs in the cavern, so where there is CMS, there are very huge sprinklers at the top of the cavern that can inject into the cavern foam through which humans can breathe, as far as I know, and that will be able to turn down any kind of fire. The problem is that if this foam is actually sprinkled, the entire electronics of the detector will be completely destroyed. So if anything happens for which the foam needs to be ejected, CMS is completely dead. We clearly don't want to do that, but they did a test of that. As far as I know, CMS is the only place in LHC in the 4 detectors where they actually did test the setup.
But with the empty cavern.
Yeah, of course, with no CMS, absolutely.
We have
with an
some
empty
nice
cavern.
That's definitely true. Actually, this system is not completely strange. It is used in warehouses, usually large warehouses, to extinguish fires there. But this is, as Giulia said, this is the last resort.
Yeah, this is the end of our
experiment. If we would need to use it, only the integrity of the underground cavern is the concerned thing, and no more the detector. Obviously, this is not an automatic system.
No. No.
Great. We have one more question. How long and difficult is to accelerate particles in LHC? That's not our business. That's the accelerator guys. But what we can tell that filling the LHC through the pre-accelerator chain takes something like a quarter of an hour,
Mm-mm.
and then another 20 minutes-ish to accelerate it up to the collision energy. Then you have to squeeze the beams and align them.
Heat knives.
Exactly. Well, making the collision of these two protons is not very difficult. It's just something like shooting through the needle of the eye of a needle when the needle is on the moon.
Yeah.
So something that can be mitigated. So obviously, fortunately, we are just the benefiting of these things. But this is one of the most complex things that have ever been made in human history. Right.
Jorge texted us that
Jorge had something
say some final words for
go
you.
ahead.
So
Yes.
I think this is the end from our side.
Yes, I think this is the end of this morning session. I want to thank you once again for giving the opportunity to worldwide students to join this session. I think it's very nice for them to see actual experiments and visit virtually the facilities at CERN, so they get inspired. So I want to thank you for giving this virtual tour to them. And for the students, just be aware that we are launching the competition for 2026. The pre-registration is open, so please visit our website, join the Facebook group, LinkedIn. I will be sending lots of emails promoting the online events. And just stay tuned for the launch of the competition 2026. And have a nice afternoon, all of you.
All right.
So I don't know if you want to say some words.
I'm also very interested in the Beamline for schools. I'm as you know, I'm a national contact. So
yes.
Definitely I need to inform my people at home. Right. It was nice to meet you. Let's continue in the evening. Right.
Nice meeting you, and see you in the afternoon. Bye bye.
Ciao, ciao,
Thank
ciao,
you.
ciao.